In the last video, we were talking about the various indeterminate forms that allow us to use L'Hopital's rule, but I was making the argument that you don't really have to have them memorized. You don't have to have memorized that 0 times infinity is an indeterminate type, nor do you have to memorize that infinity minus infinity is an indeterminate type. All you have to memorize is, if you're given a problem that kind of looks like this, try to make it a fraction and then see if it's 0 over 0 or infinity over infinity. Something very similar holds for this 0 to the 0 type. Consider the limit as x approaches 0. Maybe technically I should make this from the positive side here. Not something you really have to worry about. Of x raised up to the sine of x power. Well, let's see. When x gets really close to 0 but is slightly positive, x, the base here, is getting really close to 0. And as we've already seen, when x gets close to 0, the sine of x gets close to 0 because the sine of 0 is equal to 0. So what we have here is the 0 over 0 type, which turns out to be one of the indeterminate forms, but really is just one of these more familiar indeterminate forms in disguise. How do you see it's one of these forms in disguise? Well, you do some really clever algebra. The trick that you'll use on these type 2 problems, examples D, E, and F, is you're going to set up an equation. This thing that I'm trying to figure out, I'm going to call it y. Y is equal to the limit as x approaches 0 from the positive side of x raised up to the sine of x power. Why do you call this thing y? What's the purpose in introducing this new variable? Well, now that I have this equation, I can mess with both sides of the equation. If it benefits me, I could double both sides of the equation, because if y is the same as all this stuff, 2 times y is the same as 2 times all this stuff. It doesn't benefit me to double both sides of the equation, but doing something similar to both sides of the equation will be beneficial. What will be beneficial will be taking the log of both sides of the equation. You can take any log that you want, but the log that's most useful will be the natural log. So if y is equal to the limit as x approaches 0 from the positive side of x to the sine of x power, then the natural log of y is equal to the natural log of the limit as x approaches 0 from the positive side of x raised up to the sine of x power. And thanks to some limit laws, you can interchange the natural log and the limit. The natural log of the limit of something is the same as the limit of the natural log of something. So I can write the natural log inside here. And you're like, where's this going, right? It started out with a kind of hard-looking problem, and now it's a mess. Now you've involved logs. Like, logs are the worst. Okay, first of all, they're not the worst. Logs are awesome. But secondly, you're not supposed to see where this is going at this point. Just understand how I got from this line to this line, not why I went from this line to this line. As long as you can see what I did from the first line to the second line, we're ready to move on. We're not going to do anything to the left side of the equation, but on the right side of the equation, I'm going to do some clever algebra. What algebra am I going to do? Well, maybe you remember log rules. You're like, nope, sure don't. Okay, well, trust me that one of the log rules said that when you're taking the log of something raised up to an exponent, you can take that exponent down in front and multiply it by the log of the base. Don't think power rule here. We're not taking any derivatives. This has nothing to do with calculus. This is something you were supposed to learn in a pre-calculus class, that the log of something raised up to a power is that power times the log of the base. If somebody asks you for the log base 2 of 4 to the 10th power, you don't have to figure out 4 to the 10th power. That's some huge number. You'd never want to figure that out. What you instead do is say it's just 10 times the log base 2 of 4. And then if you're good with logs, you're like, the log base 2 of 4 is just 2. So it's 10 times 2, in other words, 20. Anyways, this log rule is very useful because what we end up with here is the log of something raised up to a power. And that has to be the case because we're in this type of problem where we have exponents. We have a variable for the base and a different variable up in the exponent. It's not specific to this example. We're going to do this method anytime we're in that case with the variable as the base and a variable as the exponent. That'll always produce something that looks like this, the log of something raised up to a power. And thanks to this log rule, we'll always be able to rewrite this as a product of two things. In this case, the sine of x and the natural log of x. Think, you're taking this sine of x and you're bringing it down in front of this natural log of x, and that gets you here. You might not recognize this, but when x gets really close to 0, sine of x gets really close to 0. And when x gets really close to 0, natural log of x gets really close to negative infinity. What we have here is the 0 times infinity indeterminate form that we saw up here in part B. Really, the strategy for part D is to first change it into a problem that kind of looks like part B, and then finish up the problem using the methods we learned up here in part B. Wait, what did we do in part B? That was the last video, right? Yeah, and in the last video, we started out with something times something and recognized that we're not going to be able to use L'Hopital's rule because it's a product. And L'Hopital's rule works on quotients. So we rewrote this thing so that it kind of looked like a fraction. That's what we're going to do down here. How do we make sine of x times natural log of x equal to a fraction? Well, there's a couple ways you can do it. We can either make this sine of x divided by the natural log of x all raised up to the -1 power, or we can make this the natural log of x divided by the reciprocal of sine of x. I think that way will be a little bit easier because the reciprocal of sine of x is a trig function that we know. The reciprocal of sine of x is the cosecant of x. Because 1 over sine equals cosecant, 1 over cosecant equals sine. So this expression is the exact same as this expression right here. We haven't done any L'Hopital's rule yet. All we've done is rewritten this expression in various forms. First, we introduced logs to change it from an exponential expression into the product of two things. And then we recognized that we'd never be able to use L'Hopital's rule on a product of two things, so we rewrote it as a quotient. If you stare at this thing, I think what you'll find is we have the infinity over infinity type. As x gets close to 0, the natural log of x gets close to -infinity, and when x gets close to 0, the cosecant of x gets close to infinity. This is the infinity over infinity indeterminate form. So we can use L'Hopital's rule. Say that this limit is the limit as x approaches 0 from the positive side of the derivative of natural log of x, which is 1 divided by x, divided by the derivative of cosecant of x. The way I remember that is I remember the derivative of secant of x is secant times tangent, so the derivative of cosecant of x is almost cosecant times cotangent. I just have to remember to put a negative in there. Is this a limit we can evaluate? I have no idea when it's written in this form, so why don't we clean it up a little bit? Instead of 1 over x up on the top, I can put an x down on the bottom. Instead of negative cosecant of x times cotangent of x down on the bottom, I can recognize that the reciprocal of cosecant is sine, and the reciprocal of cotangent is tangent. So 1 over x divided by negative cosecant times cotangent is the exact same as the negative of sine of x times tangent of x divided by x. Is this a limit that we can evaluate? I don't know, maybe. Let's check it out. If we change all our x's into zeros, the bottom's going to be 0. If we change all our x's into zeros, because sine of 0 equals 0, the top's going to be 0. This is still an indeterminate type. It's a 0 over 0 indeterminate type, unlike this one that was the infinity over infinity indeterminate type. So I can use L'Hopital's rule one more time. To use L'Hopital's rule, I take the derivative of the bottom, which is just equal to 1, and I take the derivative of the top, which is going to be kind of a pain because it's something times something, so I got to use the product rule. I got the negative of the derivative of sine is cosine, leave the tangent completely alone, and then add to that the derivative of tangent, which is secant squared, leaving the sine completely alone. Is this an indeterminate type? Again, no idea, but we can clean it up and figure it out. Tangent is sine over cosine, so cosine times tangent would just be equal to sine. This cosine and the cosine in the denominator of tangent cancel out, and then secant is 1 over cosine, so secant squared is 1 over cosine squared, so I got sine of x divided by cosine squared x. Is this an indeterminate form? Nah, fortunately, this is something we can evaluate, because when x gets really close to 0, sine of x gets close to 0. And when x gets really close to 0, cosine of x gets close to 1, and 1 squared gets close to 1. So I got 0 over 1, in other words, 0. My answer is the negative of 0 plus 0, in other words, 0. Wow, that's a lot of work just to get an answer of 0. Yeah, and guess what? We're not even done. The limit as x approaches 0 from the positive side of x sine of x is not equal to 0. You're like, wait, what? Inconceivable. We did all this work. This has to be right. Nah, this is the natural log of y, right? The natural log of y is what's equal to this limit, which is equal to this limit, and 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 this. 0 is not equal to y, the original question. 0 is equal to the natural log of y. Y is what we want to solve for, because y is the limit as x approaches 0 from the positive side of x times the sine of x. Y is the answer to the question. The natural log of y equals 0. If we do e to both sides of the equation, we get y is e to the 0 power. E to the 0 power is equal to 1. Maybe now you can see why I didn't do this in the last video, right? That's a pretty wild example. That's as hard as these problems can possibly get. Realistically, most students, if they were working on this, would make some little mistake somewhere in here with their algebra, and that's fine. That stuff happens. I just want you to understand this entire process. When we have the type of question where we got exponents in the base and exponents up here in the exponent, we're going to set up an equation, then take the natural log of both sides of that equation, and what that will give us is something times something. Our third step will be to use this log rule to rewrite this limit as a product of two things. If you can do these three new steps, really the process is something you learned in the previous video. You got something times something, so what you need to do, step 4 if you want, is rewrite that so it's something divided by something. All of a sudden, you have either the 0 over 0 or infinity over infinity indeterminate forms. So now it doesn't feel like this special case of L'Hopital's rule that we're doing in this video. It feels like the types that we've done in previous videos. You're probably a little bit overwhelmed, but I want to do 2 more examples in this video because I think what you'll find are the remaining indeterminate types, infinity to the 0 power and 1 to the infinity power, work just like this example that we just did. If you were trying to evaluate the limit as x approaches infinity of x raised up to the 1 over x power, you wouldn't have to recognize that it's the infinity to the 0 type. What you could instead do is just set up an equation. We could say y is equal to the limit as x approaches infinity of x to the 1 over x power. Now that we have an equation, we can mess with both sides of that equation. I could take the natural log of both sides and say the natural log of y is equal to the limit as x approaches infinity of the natural log of x raised up to the 1 over x power. The reason we involve natural logs is because we want to use this log rule to get rid of the exponents. We leave the left side completely alone, and on the right side, we take this 1 over x and bring it in front of the natural log. We got that the natural log of y is the limit as x approaches infinity of 1 over x times the natural log of x. Now we have something times something. It turns out it's the 0 to the infinity type, but you don't really even need to worry about that. Just rewrite it as a fraction. In this case, it's pretty easy to rewrite as a fraction. Instead of 1 over x times the natural log of x, just make it the natural log of x over x. And consider that fraction. Is this an indeterminate form? Yeah, it's gonna be. Because we originally started out with the infinity to the 0 type, we're gonna end up with an indeterminate form down here. But you don't need to know all that. Just stare at this thing. Think about what happens when x gets close to infinity. The natural log of an infinitely large number is some infinitely large number, and the denominator is just x, which is getting close to infinity. This is the infinity over infinity indeterminate form, so we can use L'Hopital's rule. It tells us the limit of this indeterminate form is equal to the limit of the derivative of the top divided by the derivative of the bottom. What's the derivative of the natural log of x? That's just 1 over x. What's the derivative of x? That's just 1. Cleaning things up a little bit, we get that this is the limit as x approaches infinity of 1 over x. What happens to a fraction when the top is a constant and the bottom is getting arbitrarily large? That fraction approaches 0. The limit as x approaches infinity of 1 over x is equal to 0, and therefore, the limit as x approaches infinity of the natural log of x raised up to the 1 over x power is 0. But remember, this is not what you're trying to figure out. This is the natural log of y that's equal to 0. The natural log of y equals 0 tells us that y is equal to 1. Do e to both sides of the equation if you want. Yes, that's the same answer we got before, and no, unfortunately, that's not always going to be the answers. You really do have to go through this process to figure out what the answer is going to be. Let's do one more. The limit as x approaches 0 of x plus 1 raised up to the natural log of 1 over x power. Technically, I should consider this from the right side. You don't really need to worry about this, but if x is slightly negative, then I'm taking the natural log of a negative number here, which is undefined. So technically, to make this question make sense, I should consider the limit from the right. If you try changing all the x's into zeros, I think what you'll find is that you have 1 raised up to infinity. But again, you really don't have to worry about that. What you do instead is set up an equation, make y equal to this expression, and then take the natural log of both sides of that equation. I got the limit as x approaches 0 from the positive side of the natural log of x plus 1 raised up to the natural log of 1 over x. Lots of natural logs floating around. It would be easy to get confused here. This natural log of 1 over x is my exponent. That's what's going to come down in front here. So I get the limit as x approaches 0 from the positive side of that exponent, which just so happens to be the natural log of 1 over x, times the natural log of x plus 1, the thing that used to be playing the role of the base. I now have something times something, which is not especially conducive to L'Hopital's rule. So what I'm going to do is just take the natural log of 1 over x and put that up on the top of the fraction. And then in order to get the natural log of x plus 1 down on the bottom of the fraction, I'm going to raise that entire thing to the negative 1 power. There might be some clever log trick you can do here, but nothing's jumping out at me. Let's look at what's happening here. When x gets close to 0 from the positive side, 1 divided by something close to 0 from the positive side is infinite. The natural log of something that's infinite is infinite. Down on the bottom, when x is getting close to 0, x plus 1 is getting close to 1, and the natural log of 1 is getting close to 0. 0 to the negative 1 power means 1 divided by 0, and when you have a non-zero constant like 1 divided by something getting really close to 0, you end up with infinity. What I have here is the infinity over infinity type, so I can use L'Hopital's rule. To use L'Hopital's rule, I have to take the derivative of the top and the derivative of the bottom. There's a few options for how you take the derivative of the top. I think the clever way would be to recognize that 1 over x is the same as x to the negative 1 power. So you're taking the log of something raised up to an exponent. You could bring that exponent down in front. It's the negative of the natural log of x. So since the natural log of 1 over x is the exact same as the negative of the natural log of x, it might be easier to take the derivative of this thing instead of the derivative of this thing. I suspect most students would not make that connection, and they would just try to power through this using the chain rule to take the derivative, so I'll do it that way. Taking the derivative of the outer layer, the natural log part, since the derivative of natural log of x is 1 over x, the derivative of the natural log of 1 over x is 1 divided by that 1 over x thing. But then I'm not done. I have to multiply that by the derivative of 1 over x. If you view that 1 over x as x to the negative 1 power, then maybe you're okay with rewriting that derivative as negative 1x to the negative 2 power using the power rule. Don't worry, it'll turn out this will simplify really nicely. Down on the bottom, I'm again going to have to employ a chain rule. My outer layer is the stuff raised up to the negative 1 power, so I'll bring that negative 1 down in front and leave the inner layer completely alone. And my new exponent will be 1 less than that negative 1, in other words, negative 2. But then I'm not done. I have to multiply that by the derivative of the inner layer. What's the derivative of the natural log of x plus 1? It's 1 over x plus 1 times the derivative of x plus 1, but the derivative of x plus 1 is just 1. We took the derivative of the top and the derivative of the bottom. Things blew up a little bit and it looks really ugly, but I think this will simplify really nicely. Let's see what happens. 1 divided by 1 over x is just x. X to the negative 2 is 1 over x squared. So I have x divided by x squared. I can cancel the x from the top and the x from the bottom, and I just get 1 over x, and it's negative because this was positive and this is negative. Oh yeah, that makes sense. If I had taken the derivative of the negative of the natural log of x instead of the derivative of the natural log of 1 over x, I'd expect to get negative 1 over x as my answer, which is exactly what we see here. Down on the bottom, I got a huge mess, but maybe you recognize that that mess is going to be negative for this negative, so we can cancel out that negative with the negative that I wrote up here, making the top positive 1 over x. This natural log of x plus 1 to the negative 2 power, I can think of as 1 divided by the natural log of x plus 1 squared, and I have to multiply that by 1 over x plus 1. We got a huge mess of stuff here, but I think we can rewrite stuff taking advantage of some reciprocal properties. Instead of 1 over x up on the top, I could just have an x on the bottom. Instead of having 1 over the natural log of x plus 1 squared down on the bottom, I could have the natural log of x plus 1 squared up on the top. And then instead of having 1 divided by x plus 1 on the bottom, I could just have an x plus 1 on the top. If we're really lucky, this will not be an indeterminate form and we can just determine our answer. Unfortunately, we're not really lucky because as x gets close to 0, the bottom clearly gets close to 0. And the top, this gets close to 1. But this gets close to the natural log of 1, which is equal to 0. And 0 squared is equal to 0. This is the 0 over 0 indeterminate form. Sadly, we have to use L'Hopital's rule one more time. The nice thing is the x on the bottom, when we take its derivative, just turns into a 1, so we don't even have to worry about that. Up on top, we got a product of things, so we'll have to use the product rule, and that's going to get kind of ugly, so maybe I can jump down here to the next page. I'm taking the derivative of something times something, so I take the derivative of the first thing. The derivative of that first thing involves the chain rule, so first the outer layer, the stuff being squared, I bring the 2 down in front, and then I have the natural log of x plus 1, now raised up to the first power, which I don't even have to write, times the derivative of that inner layer. The inner layer is the natural log of x plus 1. Its derivative is 1 divided by x plus 1 times the derivative of x plus 1, which is just equal to 1. This expression is the derivative of this thing. Remember, I'm inside the product rule here, so I take that derivative times this x plus 1 left completely alone, and then I add to that the derivative of x plus 1, which is just 1, times this first term left completely alone, the natural log of x plus 1 squared. Can we clean this up a little bit? Absolutely we can. This x plus 1 and this x plus 1 cancel out, so I have 2 times the natural log of x plus 1 plus the natural log of x plus 1 squared. Mercifully, I think this is not an indeterminate form because as x gets close to 0, x plus 1 gets close to 1, and the natural log of 1 gets close to 0. So I have 2 times 0 plus 0 squared. I end up with just 0. Whew, finally I'm done. Nope, you're not. Wait, what? Yeah, this isn't y that we just solved for. This is the natural log of y. For the third time, it won't always be the case, but for all three of the examples we've seen, the natural log of y equals 0. Therefore, e raised up to the natural log of y equals e to the 0, and e raised up to the natural log of y is just equal to y. What I'm saying is y is equal to e to the 0 power, in other words, 1. The limit as x approaches 0 from the positive side of x plus 1 raised up to the natural log of 1 divided by x power is just equal to 1. What's the takeaway from this video? Well, first of all, that this second type of problems that you can do with L'Hopital's rule are exceedingly difficult. Any Calculus 1 student who can do the work in red or the work in purple or the work in brown without making a mistake is way ahead of where they should be as a Calculus 1 student. Where you should be as a Calculus 1 student is being able to follow the steps if somebody else does them and being able to recreate the steps on your own, allowing yourself to make minor algebraic mistakes as you go through. And as long as that's what you're getting out of this video, I think we're good.